the universe stands as a grand and mysterious stage that has inspired endless human imagination and a deep desire for exploration since ancient times. From the sun, moon, and stars visible to the naked eye to the distant galaxies captured by our most powerful telescopes, our understanding of this vast expanse continues to deepen. The story is long, and perhaps best told in dreams, but before we begin, remember to like and share this journey. Ancient ancestors looked up at the starry sky and wove myths and legends, endowing the universe with life and will. Later, the philosophers of ancient Greece began to use rational thought to consider the composition of the universe, proposing early physical concepts such as atomism. By the 17th century, Sir Isaac Newton, with his law of universal gravitation, for the first time accurately described the common laws governing both the stars in the sky and the falling of an apple on Earth. He unified heaven and earth within a concise and universal mathematical framework. Gravity was no longer seen as the will of a deity, but as an inherent property of mutual attraction between cosmic matter. This was undoubtedly a milestone in human understanding. Consequently, the celestial and terrestrial were linked, and the faint starlight we observe became more informative through macro perspectives. Then came a name that would delve into the deepest mysteries of gravity, Albert Einstein. As one of the greatest physicists of the 20th century, his genius insights overturned the Newtonian view of gravity. In Einstein's general relativity, gravity is no longer a force but rather the curvature of space-time itself. Imagine a heavy bowling ball placed on a trampoline, the fabric curves downward. Any marble rolling near it will follow the curve of the depression rather than a straight line. In general relativity, the bowling ball represents mass and energy, the trampoline represents space-time, and the marble represents light and planets. They follow curved paths not because they are pulled by a force, but because they are moving along the shortest path in a curved space-time. General relativity greatly broadened our understanding of the cosmos, successfully predicting the bending of light, the perihelion precession of Mercury, and gravitational redshift. It was finally validated at the end of the last century through the detection of gravitational waves. It also painted a grand blueprint for cosmic evolution, from the Big Bang to the formation of galaxies and eventually to expansion and decay. Despite the immense success of general relativity on a cosmological scale, it encounters bottlenecks under extreme conditions. When the density of mass and energy becomes extreme, such as inside a black hole or at the initial moment of the Big Bang, the descriptions of general relativity fail. A deeper contradiction lies in the fact that quantum mechanics, which describes the microscopic world, and general relativity, which describes macroscopic gravity, seem to be two incompatible theories. Each has achieved stunning success in its own realm, yet they clash violently when one attempts to unify them. For instance, quantum mechanics emphasizes the conservation and indestructibility of information, while the black holes predicted by general relativity seem to swallow all information, leading to the famous black hole information paradox. Furthermore, observations of the accelerated expansion of the universe and galaxy rotation curves suggest the existence of dark energy and dark matter, which we do not yet understand. These unsolved mysteries drive scientists to explore new theoretical frameworks to achieve a more comprehensive and unified understanding of the deep order of the universe. Against this background, two cutting-edge theoretical concepts have emerged: the holographic principle and anthropic gravity. These two theories examine the nature of the universe from unique perspectives and may provide breakthrough solutions to the aforementioned puzzles. The holographic principle suggests that the three-dimensional universe we perceive may not be its most fundamental state, but rather an information projection encoded from a lower dimensional boundary, much like a two-dimensional holographic photo that presents a three-dimensional image. Anthropic gravity, on the other hand, proposes an even bolder idea, that gravity is not a fundamental force, but a macroscopic phenomenon emerging from information or entropy and temperature gradients within space-time. This challenges our deep-seated perceptions of gravity, likening it to gas pressure or liquid tension macroscopic effects resulting from the statistical behavior of a large number of microscopic particles. This discussion will delve into these complex and fascinating theories, guiding you step by step to reveal how they challenge traditional views and open new paths for understanding the fundamental properties of the universe. In the vastness of the cosmos, black holes are undoubtedly among the most mysterious and extreme celestial bodies. Their birth marks a magnificent yet tragic finale to a star's life. When a massive star exhausts its internal nuclear fuel, it can no longer support its own immense gravity, leading to a violent gravitational collapse. During this process, the star's matter is compressed until the density at a point in space-time becomes infinite. This is the singularity, the starting point of a black hole. The singularity is surrounded by a boundary called the event horizon. The event horizon is the defining feature of a black hole, a one-way boundary. Once any matter or light crosses this threshold, it can never escape the powerful gravitational pull. As the name suggests, it is the horizon of events, meaning we cannot see anything happening inside from the outside because even light cannot escape to carry information. For a long time, it was believed that black holes were the ultimate scavengers of the universe, where things went in but never came out. However, in the 1970s, the renowned physicist Stephen Hawking proposed a theory that shocked the world: black holes are not completely black. They actually emit faint radiation, now known as Hawking radiation. This radiation is a result of quantum mechanical effects near the event horizon, causing the black hole to slowly lose mass and potentially evaporate completely. This discovery was revolutionary because it linked black holes, purely objects of general relativity, with the quantum theory of the microscopic world. Yet, the discovery of Hawking radiation immediately led to a deeper contradiction: the black hole information paradox. In quantum mechanics, a fundamental principle called unitarity states that information is conserved in any quantum process, it cannot be created or destroyed. This means that no matter how a system evolves, all its initial information should be preserved in some way. For example, if you burn a book, its physical form disappears, but the information regarding every atom and its internal state still exists in the ash and smoke. Theoretically, we could recover the book's information by analyzing these remains. But when we apply this to a black hole, a problem arises. If a book falls into a black hole, all its information seems to plummet into the interior. If the black hole eventually evaporates via Hawking radiation, and that radiation is purely thermal and carries no information about the interior, then the original information appears to be lost forever. This directly violates the principle of unitarity. The importance of this paradox cannot be overstated. If information can truly be destroyed, the very foundations of quantum mechanics would be shaken, suggesting a massive hole in our understanding of the basic laws of the universe. Traditional gravity theory suggests that black holes have no hair, meaning they have no features other than mass, charge, and angular momentum to encode information. This makes a black hole look like a giant information shredder. Physicists have exerted enormous effort to solve this, as the paradox touches upon the core unification of physics. It was through deep reflection on this paradox that a new, disruptive idea began to sprout: the holographic concept. The initial clues came from the study of black hole entropy. The work of Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole, a measure of its internal disorder, is proportional to the surface area of its event horizon rather than its volume. This differs greatly from our daily understanding, where the entropy of an object usually scales with its volume because a larger volume can accommodate more microscopic states. The fact that black hole entropy relates to area strongly implies that all the information of a black hole is not distributed within its three-dimensional interior, but is encoded on its two-dimensional surface. This led physicists to wonder, if black hole information can be stored on a 2D surface, could all the information in the universe be encoded on a distant 2D boundary? This is the core of the holographic idea that 3D information can be fully encoded on a 2D surface. Dutch physicist Gerard 't Hooft and American physicist Leonard Susskind were key proponents of this, suggesting that all information in the universe might be projected on a lower dimensional boundary. This provides a possible exit for the information paradox. Perhaps information does not disappear in a black hole but is projected onto the event horizon. This opening of a new door suggests that our exploration of the nature of the universe is entering an unprecedented dimension. Following these breakthroughs, the holographic concept evolved into a profound physical principle. 't Hooft was the first to explicitly propose it, and Susskind further developed it into a universal law. The idea is subversive. The 3D universe we perceive, or any 3D region within it, does not store its information at every internal point, but rather maps it to a 2D boundary. To understand this, we look again at a hologram, a flat photo that records all the light wave information of a 3D object, allowing us to see depth from different angles. The holographic principle applies this to the very nature of the universe, suggesting our 3D experience might be a projection of higher dimensional information on a lower dimensional surface, like a 2D movie screen making us feel a 3D scene. If the holographic principle provides a way out for the paradox, its greater significance lies in providing a path to unify general relativity and quantum mechanics. A major milestone here is the AD/CFT correspondence, proposed by Juan Maldacena in 1997. This theory acts as a bridge, establishing a precise mathematical correspondence between a gravity theory in a curved spacetime, anti-de Sitter space, and a quantum field theory without gravity, conformal field theory, on its boundary. To understand this, we must mention string theory and M-theory, which attempt to unify all particles and forces by suggesting the basic constituents of the universe are not point particles but tiny vibrating strings. Maldacena's duality revealed that a difficult-to-handle strong gravity system can be described by a relatively easy-to-calculate quantum system without gravity. It is like a precise translator, allowing physicists to switch between two different physical languages. This solved a long-standing problem. When gravity is strong, the equations of general relativity become too complex, and when quantum effects are significant, quantum mechanics is incompatible with gravity. The AD/CFT correspondence allows us to perform calculations in a weakly coupled quantum field theory and map the results to a strongly coupled gravity theory. It is a powerful tool for studying quantum gravity, the microscopic structure of black holes, and the early state of the Big Bang. This duality has even permeated other fields like condensed matter physics, helping researchers understand complex materials like high-temperature superconductors by mapping them to gravitational theories. This cross-disciplinary application demonstrates the vitality of the holographic principle. It brings profound philosophical implications, challenging our perception of reality. If it is correct, our 3D universe of stars and planets may not be the fundamental form, but a giant hologram, an illusion projected from lower dimensional information. While it sounds like science fiction, it has solid mathematical foundations. In this view, information becomes the most fundamental constituent of the universe, more so than matter or energy. Information is conserved, and the complexity of the universe can be traced to a simpler boundary. This is a huge challenge to our senses, as we are used to describing everything in terms of length, width, and height. However, the progress of science often involves the subversion of intuition. From the Earth revolving around the Sun to particles being in multiple places at once, the history of physics is full of examples where intuition was challenged and eventually proven wrong. The holographic principle is the latest example of this disruptive thinking, forcing us to rethink the nature of the world we live in and whether the reality we perceive is merely a local projection of a vast cosmic hologram. In our exploration of the deep order of the universe, gravity has always held a central position. From the gravity of the Earth beneath our feet to the gravitational forces between distant galaxies that shape the cosmic structure, gravity is everywhere. Our understanding of it has undergone several revolutionary leaps. Sir Isaac Newton's law of universal gravitation in the 17th century used a concise mathematical form to accurately describe the motion of objects under macroscopic, low-speed, and weak gravity conditions. He revealed that gravity is a force acting instantaneously between objects, with a strength proportional to the product of their masses and inversely proportional to the square of the distance. Newtonian gravity dominated for centuries, explaining planetary motion and tides. However, in the early 20th century, Einstein's general relativity completely overturned this traditional view. He no longer saw gravity as a force, but as the curvature of the space-time fabric caused by matter and energy. Imagine a large iron ball on a stretched rubber membrane, the membrane curves inward, and any marble will follow that curve. In this analogy, the ball is matter/energy, the membrane is space-time, and the marble is other matter or light. General relativity succeeded not only in explaining what Newton could but also in predicting phenomena Newton couldn't, such as the bending of light in a gravitational field and the slight precession of Mercury's orbit. The discovery of gravitational waves provided the most direct experimental evidence for this theory. Evidence confirms that the ripples of space-time truly exist and can be detected. Although general relativity has achieved immense success on a cosmological scale, it is not without limitations. Under extreme conditions such as at the center of a black hole or during the initial moments of the Big Bang, the descriptions provided by general relativity begin to fail. More importantly, there is a fundamental conflict between general relativity and quantum mechanics, which describes the microscopic world. Quantum mechanics, with its principles of probability, uncertainty, and the discrete nature of energy and matter, is incompatible with the continuous, geometric space-time of general relativity. Physicists have long struggled to find a theory of quantum gravity to unify these two pillars, but the path has been exceptionally difficult. It is within this context of seeking quantum gravity and a deeper understanding of black hole thermodynamics that a bold new conceptualization of gravity emerged: anthropic gravity. To understand anthropic gravity, we must first revisit the concepts of entropy and thermodynamics. Entropy is a measure of disorder or randomness within a system. The higher the entropy, the greater the internal chaos. The second law of thermodynamics tells us that in an isolated system, entropy always tends to increase, meaning systems move from order to disorder. This law governs many daily phenomena, such as hot water cooling or a room warming. The first major clue linking thermodynamics to gravity was black hole entropy. The work of Bekenstein and Hawking showed that the entropy of a black hole is proportional to its event horizon's surface area. This suggests a deep connection between gravity and thermodynamics. If a massive gravitational object like a black hole stores its information and entropy on a two-dimensional boundary, could gravity itself be a macroscopic thermodynamic effect? Reflecting on this, Dutch theoretical physicist Erik Verland proposed the theory of entropic gravity in 2009. His core idea is subversive: gravity is not a fundamental force of the universe, but rather a macroscopic phenomenon emerging from information, or more accurately, from entropy and temperature gradients within space-time. To better understand this emergence, we can look at familiar macroscopic phenomena. For instance, water has surface tension, allowing droplets to stay spherical and insects to walk on water. Surface tension is not a fundamental force between individual molecules, but a macroscopic effect resulting from the statistical interactions of a vast number of water molecules. Similarly, gas pressure is not a fundamental property of a single molecule, but the macroscopic manifestation of countless molecules colliding with container walls. Verland argues that gravity might be exactly such an emergent phenomenon. It is not a force directly transmitted between particles like electromagnetism or nuclear forces. Instead, it is a macroscopic effect produced by the collective behavior of fundamental information bits, or the entropy that constitutes space-time. Within the mathematical framework of entropic gravity, Verland introduced the concept of holographic screens. He envisioned a giant, reinforced holographic screen in the universe, similar to a black hole's event horizon, encoding all information in space-time. When information on this screen changes, entropy changes, leading to temperature gradients that produce the gravity we experience. Think of it as a reaction force generated when you try to move information bits on this screen. That reaction is gravity. Through rigorous derivation, Verland showed how Newton's law of universal gravitation, and even Newton's second law, where force equals mass times acceleration, can be derived from information, entropy, and temperature gradients. This implies that the formulas we consider fundamental physical laws may actually be results emerging from deeper dynamics of entropy and information. This derivation process is ingenious, using insights from black hole thermodynamics and the holographic principle to link microscopic information movement with macroscopic gravitational effects. Entropic gravity not only offers a new explanation for the nature of gravity, but also provides a more natural framework for explaining major mysteries like dark energy and dark matter. We know the universe's expansion is accelerating, usually attributed to a mysterious dark energy that makes up about 70% of the total energy density. In the framework of entropic gravity, accelerated expansion may not require extra dark energy. Instead, it could be a manifestation of gravity itself on a cosmic scale, or the collective effect of information and entropy at macroscopic scales. Similarly, regarding the mystery of dark matter, entropic gravity offers an alternative explanation. Observations show stars at the edges of galaxies rotate faster than predicted by visible matter, suggesting invisible dark matter exists. In modified versions of entropic gravity, this extra gravitational effect might not be caused by a new particle, but by differences in how gravity behaves at different scales. In other words, the law of gravity might deviate slightly from general relativity on galactic scales due to the distribution of entropy and information in space-time. Entropic gravity undoubtedly poses a massive challenge to our physical worldview. It demotes gravity from a fundamental force to an emergent phenomenon. If correct, the fundamental constituents of the universe are not particles and forces, but information and its flow. This elevates the status of information to the cornerstone of the universe. While currently in a development stage requiring more mathematical refinement and experimental evidence, the new perspective it opens for building a unified quantum gravity theory is exciting. It prompts us to consider if the gravity we perceive is merely a shadow cast by changing information on a vast cosmic hologram. We have explored the holographic principle and anthropic gravity as two separate yet interconnected threads. The holographic principle starts from the black hole information paradox and suggests that universal information is encoded on lower dimensional boundaries, with the AD/CFT correspondence providing a solid mathematical framework. Anthropic gravity views gravity as an emergent phenomenon from that information. These two theories are highly complementary, both rooted in black hole thermodynamics. The holographic principle serves as the deeper background. If all information is on a distant 2D boundary, it becomes logical for gravity to emerge as a macroscopic effect from the interaction and flow of these information bits. The success of the AD/CFT correspondence indirectly supports this, as describing a strong gravity system via a quantum field theory without gravity implies that gravity is the collective behavior of quantum degrees of freedom, that is, information. However, both theories lack direct experimental evidence, a challenge faced by all frontier physics. Just as general relativity required decades to be verified by Eddington's observations of light bending and the detection of gravitational waves, these theories need empirical testing. Their potential to explain dark energy and dark matter may be the key to their validation. If future cosmological observations find that expansion patterns or galactic gravitational lensing align better with modified gravity models based on entropy than with traditional dark matter or energy models, it would provide significant support. Future directions include precise measurements of the cosmic microwave background, large-scale structures, and supernovas to distinguish between gravitational theories. Further development in gravitational wave detection, such as space-based observatories, may reveal subtle behaviors in extreme conditions that differ from general relativity but align with holographic predictions. Particle accelerators, though seemingly unrelated, may also provide clues about quantum field theory that inform quantum gravity. The impact of the holographic principle and anthropic gravity on cosmology and fundamental physics is profound. They provide a new path toward a unified theory. If gravity is an emergent phenomenon, we no longer need to search for the graviton, a hypothetical particle for gravity. Instead, we turn our attention to the nature, storage, and dynamics of information itself. This would fundamentally change our perception of the universe's constituents, placing information alongside matter and energy. Our 3D universe would then be a giant holographic projection driven by deeper laws of information and entropy, a giant information processing system. This cognitive shift would be a Copernican-style revolution, offering a new interpretation of the nature of the universe and our existence. These theories remind us that the boundaries of scientific exploration are endless. They require global cooperation, diverse research, and open exchange to solve the remaining puzzles. Regardless of whether they are fully verified, they have enriched our worldview and expanded our thinking. They urge us to look at the world from a fresh perspective, bridging the gap between general relativity and quantum mechanics. The journey to explore the holographic universe is an exciting chapter in human history, potentially redefining our relationship with the cosmos. We share this knowledge today and hope it brings you wonderful dreams and a beautiful day. We will see you in the next episode.